This is HL Paper 3 question 6, which is a fantastic question all about binding energy. First of all, definition of binding energy. There are two possible answers. It's either the energy required to pull apart a nucleus into its constituent particles, or alternatively, the energy that is released when a nucleus forms from its constituent particles. If you don't know that by now, your physics teacher will be furious. B then says we've got this reaction here. We've got uranium going to barium, krypton, and a neutron or a number of neutrons. Use the graph to show that the fission of one nucleus will release about 200 MeV of energy. Right, so we need to look at the difference in the binding energy. So uranium-235, when we look that up on this graph, we've got 230. So 235 is about here. If you go up to the line and then across, that gives us a binding energy per nucleon for uranium of 7.6. To get the total binding energy, we multiply that 7.6 by 235. That's the number of nucleons in uranium to get this as a total binding energy for one nucleus. You do the same with krypton and barium, very carefully drawing lines up and across to find out the binding energy. And you'll find that there is a difference in the binding energy of 198 MeV. It's really important to say that it's 198 and not 200 because that's already given in the question. Always give more detail than any show that question. It then says state the value of x in the equation. All you need to do is make sure that the top numbers and the bottom numbers add up. Well, the bottom numbers in this case we don't care about because neutron has got 0 on the bottom. We've got 235 goes to 141 and 92, so all we need is an additional 2 to get 141 plus 92 plus 2 is 235. It then says thorium-227, which is one of the products I think, undergoes alpha decay with a half-life of 18 days, so that's T1/2, to form radium-223. It has an initial activity, so A0, of 3.2 times 10 to the 5. We need two equations for this. The first one is the equation for activity and how it relates to time. So A equals A0 e to the minus lambda t. So this is what causes it to decay. And we also need the fact that lambda, the decay constant, is equal to ln2 over T1/2. Well, ln2 divided by 18. I'm deliberately going to leave it in days here, but you can convert it to time. To seconds. The only problem with converting it to seconds is that you'll need to do that for both. If you're doing it for both, there's no point in doing it at all. So we do ln2 over 18 to get a decay constant of 0.039 per day, if that makes sense as a unit. Plug that into the equation above. So we got 3.2 times 10 to the 5, which is our initial activity, times it by the exponential of minus 0.039, our decay constant, times by 50, which is the number of days which have passed. That comes out as 4.5 times 10 to the 4 becquerels. Clearly, the activity should be less than the initial activity as it decays. So this is an answer that makes sense.